Hello all, welcome to the next video of Boolean Algebra. In the last videos we have seen what is Boolean logic, what are the different laws in Boolean logic, different logic gates we saw, and we saw the truth tables also. So in this video we will be learning about the De Morgan's law of the Boolean logic, and we'll see some of the Boolean algebra rules that we have learned earlier. And one more, I'll be introducing you with one more gate, which is XOR gate. So moving to the De Morgan's first theorem, there are two theorems actually. The first theorem states that x plus y the whole complement is equal to x complement dot y complement. So this is the first theorem. And it has been demonstrated or realized with the help of the two gates. How many gates are here? Two gates here. One OR gate and the second is an inverter here. So here the same thing has been again, the LHS is drawn here and the RHS is drawn here. So according to the complementarity law, P plus P dash is equal to 1 and P dot P dash is also equal to 1. So this they have shown you the proof also, and the realization is also given here with the help of table. So this is the first De Morgan's theorem, and we have the second De Morgan's theorem coming. So this is a proof for the first part of the theorem. We have already told you that we have the LHS here, and the LHS is again written in some other format based on the laws we have learned. We have learned the distributive law, we have learned the complementarity law, and we have learned the properties of zeros and ones. So with the help of those laws, we have already proved it. We have proving that LHS is equal to 1. We have the RHS of the theorem as 1, and we are proving the LHS of the theorem as 1 with the help of the properties of 0 and 1, and also with the help of the distributive laws. How does it work that the distributive law works here? We can see that you know that LHS is x plus y plus x dash y dash, and based on this law we are just replacing that x plus this one, that is this is considered as A and this is considered as BC. This is considered as BC. So based on this distributive law they are changing it. So this is how it's being changed. So coming to the next theorem. This is the second part of the theorem, that is first theorem itself, it is the second part. Similarly with the help of the same thing, that is the same laws, we are trying to prove the second law also based on the different laws we have. All you have to do is based on these laws just replace line by line, that's all. Now this is the second theorem which states that x dot y dash is equal to x dash plus y dash. Here also they have demonstrated with the help of the logic gates and some algebraic theorems. Please go through it. With the help of the laws that we have learned, we can prove that the LHS is equal to 1. So this is the second part of the same theorem. There is also the procedure is same. Just pause the video. See how these laws are being implemented in each line. Now coming to just a revision of all the rules, we have the properties of zeros and ones, the idempotent law, the involution law, the complementarity law, and the commutative law, associative law, distributive laws, absorption law, and we have 3 distributive laws, and also we learned about the De Morgan's theorem. And all these laws are used for proving any or realization of any expressions or just reducing the expressions, etc. Now I'm going to introduce you with an XOR gate. XOR gate produces output 1 for only those input combinations that have odd number of ones. See, consider this is a 2-input gate where you have X and Y, that is 2 inputs. When there you have odd number of ones, you will get the output as 1. See, the truth table is also given here. When there is odd number of 1, the output will be 1. When there is an even number, the output will be 0. So this is more evident in the 3-input XOR gate. Here you can see the truth table for the 3-input XOR gate. Here you can see that for the odd ones, you will be getting the output as 1. For even ones, you will get the output as 0. Moving to the next session where you have to prove the logical expression with the help of truth tables. Here what you are going to do, the question will come like this, that verify the following expression. That is whether you have to check whether the LHS is equal to RHS. So what you have to do is, you have to draw a truth table with the number of variables in it. First you have to draw the number of variables. How many variables are here? So you should have, firstly you should have an A, table with A, then you should have B. Again you can see how many terms are there in the LHS. A bar you have to calculate, then you have to calculate B bar, find out B bar, all this in a truth table. Okay, you are drawing it in a truth table. So how many combinations will be there for 2 variables? 2 variables, there will be 4 combinations. That is 0, 0, 0, 1, 1, 0 and 1, 1. These are the 4 combinations that you get, and from this itself you can calculate the other one. Then after this, you see, you have to first find out A bar plus B bar. So 1 is done. Again you have one more thing. What is that? A plus B. So you need a column for A plus B. So A plus B is there. Again, is it finished? No. You have to find these term also. So what you have to do, again you need a column for A bar, these 2 columns. Add these 2 columns and write it here. Is it finished? No, because only LHS is finished now. Now you should have this 2 also. So go for these 2 also. That is A slash, you have the A slash here and you have the B slash B here. So A slash B will be one column. Will be one column, and A dot B will be, B slash will be another column. So go for all these columns in the truth table, and one more will be there. That is to put all these together, one more column will be there. So we'll see how it works and how it comes out. See, this is how it is done. You can see that for each and every terms in the expression we have to draw that, and which are the things that we have to check. We have to find out this column should be equal to this column. So we have proved with the help of truth table that the LHS is equal to RHS. What you have to do is just go for the combinations of all the input variables. Here only 2 variables was there, so 4 combinations are there. And go for the table columns for all the possible combinations here. So there we have to find out A dash, first we have to find out B dash, then add those 2 columns. Again A plus B has to be found out, then the LHS, the whole expression A dash plus B dash dot A plus B has to be found out. Again going to the right hand side also you have to do the same thing, go for A dash dot B, then find out A dot B dash, then add those 2 for the last one. So the columns that we have to be checked is, we have to check whether both are same is this column, that is A dash plus B dash dot A plus B is equal to A dash dot B plus A dot B dash. So hence it is proved. Now how will you solve using the logic gates? So this is the first question. You have to draw the logic circuit for the following. For OR operations, you can use the OR gate, and for AND operation, you have to use the AND gate. You see, this is how it's coming. For inversion, you can use the inverters. 3 inputs are there, so using the 3 input OR gate, and you are using a 2 input NAND gate. AND gate. So this is answer. Just try it in your notebook. Now how to write an equivalent Boolean expression from the following circuit. You can see that 3 inputs are there and see the gate. First you go for the first number gate. Here first you have second, third, fourth, 5 and 6. So just go one by one. You can see that what will be the input here. The input here will be B, and what will be the input here, because it is A is passed through an inverter, the input will be A dash, and what will be the input here, it will be direct A. Here you will get the B, and here you will get again B dash, and here you will get C. So what will be the output of this one? Since it's an AND gate, you will get as A dash B. So here it is A dash B, and here you will get direct AB since it's an AND gate. Here you will be getting B dash C. Similarly, all these inputs comes here, since it is an OR gate, all these terms will get add. We'll see how it works. So this is basically the method how you go for the realization using or finding out the Boolean expression from the logic circuits. You can see the answer is A bar B plus AB plus B dash C. There is no F here. It is accidentally from this F. So the answer is A bar B plus AB plus B bar C. That's what we all got, right? So this is just for your information. This is a logic circuit for following expression, that is using only NAND gates. The NAND gates usually NAND gates and NOR gates are known as universal gates. Why? Because only with the help of NAND gates and NOR gates, only with the help of NAND gates we can realize all the other gates, that is OR gate, NAND gates, inverter gates, that is negation. All these things can be done with the help of NAND gate. Similarly, it can be done with the help of NOR gate also. That's why they are known as universal NAND gates. This is just for information. Please go through it. Thank you.